and both Vt and mu and Cox vary with temperature. I mean, knowing how much this varies and how much Vt varies, you can calculate the minimum and maximum quite easily. Okay, the range of GMs may be quite large. So you want an amplifier of gain 10, you could be getting anywhere between 5 and 20 or something. Okay, so we would like to keep a tighter control of the gain or GM. So what do we do? So for this, let's examine the expression for GM. ID, I will use the simpler expression without channel length modulation or lambda. So this is VGS minus VT square times the current factor, and GM, the expression we have been using is mu and Cox W by L VGS minus VT. Now from this we can write VGS minus VT as square root of 2 times ID. All I am doing is to solve for VGS minus VT here, just write yourselves, by mu and Cox W by L. And if I substitute that in there, I will get another expression for GM, which is square root of 2 times mu and Cox W by L times ID. Okay. And finally, I can also write this as, simply by examining this expression and this one, yet another way of expressing VGS minus VT could be all I did was to rearrange the terms. I have not written VGS minus VT in terms of ID alone. VGS minus VT appears in both places, but this expression is correct. It's just a rearrangement of this. And if I substitute that in here, this part will get cancelled out and I'll get 2 times ID divided by VGS minus VT. So I have 3 different expressions for GM, this one, that one and that one, and all of them are correct. Of course, they are merely rearrangements of the same expression, but each one is useful in a different context. If we hold VGS fixed, okay, then clearly it makes sense to use this. Okay, there are no other hidden variables, there is only one VGS, which is the operating point term in here, and that is fixed. So then you use this, it's very easy. Okay, so if you know the current factor and the threshold voltage, you can find out the GM. Okay. Now, if by some means, if for a given ID, for a fixed value of ID, we want to calculate the value of GM, we can use this one, because ID is the only operating point term in this, right? There are no other operating point terms here. And this one, it is sometimes useful for making some calculations, we will see that later, but it has both ID and VGS. Okay. Now let's mainly look at this one and that one. Earlier we were using this, but there is one special thing about this, okay, the second expression. Okay. What is that? If I write it like this, let me call this as current factor Kn. So in this, both Kn and Vt appear. And if you look at this one, only Kn appears. Okay, this expression is independent of the threshold voltage. Okay. So now, what does it mean? For instance, imagine this scenario. We will later say how to come up with circuits that do this. The first one you already know, how to fix the a gate source voltage. Okay, we can apply a voltage source between gate and source, and in practice we use a resistive divider operating from a higher voltage and apply that voltage to the gate and source. So let's imagine a scenario where VGS is fixed at 3 volts. Remember, what we are now trying to do is to find out the effect of variation of transistor characteristics. Okay, so you imagine that you have a test setup where you set the value of VGS to be 3 volts and VDS to be something so that it's in saturation region, and you can measure all kinds of things about the transistor. Okay, so I set VGS to be 3 volts and I can find the GM of this, ID of this, and of course everywhere the assumption is that the transistor is in saturation. Okay, so that's assumed. So now we saw that as VT changes, in this case as VT changes, GM will change. Okay, because VGS is fixed, if VT is changing, this will change, and if the current factor changes, also the GM will change. Okay. So if VT changes by some delta VT, that is, we originally had this value of VT and it becomes VT prime and the difference is delta VT, then GM prime would be mu n Cox WL VGS, which is fixed, minus VT minus delta VT. Okay, and GM prime divided by GM would be, remember, just this part is the original GM. This is 1 minus delta VT divided by VGS minus VT. Okay, because GM originally was, GM was the same expression without this delta VT. All I am doing is divide GM prime by the original GM and I get this relationship. Okay, and similarly, if Kn changes to Kn prime, what happens? GM prime would just be Kn prime times VGS minus VT. By the way, I am assuming that in the first case only VT has changed and Kn has not changed, and in the second case I am assuming that only Kn has changed, the current factor has changed and the threshold voltage has not changed. In practice, of course, both will change, but this is a useful way of calculating the effects separately. Then in this case, GM prime divided by GM, that is the new value of GM compared to the original value of GM, is just Kn prime divided by Kn. Okay, so this gives you the relative change in GM when VT changes. Okay, and you can see that if you operate with a small VGS minus VT, this effect will be even more for a given delta VT. Okay, and here the ratio of change GM to the original GM is simply the ratio of current factors. Okay, this is the scenario for a fixed VGS. Okay, so now let me do something else. Let me examine the scenario for a fixed current. I'll explain exactly what I mean and later we'll see how to get that. What I mean in this case is that I take my transistor. Okay, remember originally it had to have 3 volts and a current of 200 microamperes, and my method was to just apply 3 volts between gate and source and hope that the current is 200 microamperes and GM is 200 microsiemens and so on. So now I'll try an alternative strategy. When I buy a transistor, I don't know what its VT is, etc., etc. So what I'll do is I'll apply some VGS which is variable. Okay, and I'll have an ammeter here and I'll set the value of VGS which will give me a current of 200 microamperes. By the way, I am not showing the whole circuit here. We can't leave the drain open circuited and so on. Okay, it's assumed that it is connected somewhere. It's connected to a voltage source which establishes VDS and so on. Okay, so maybe I will show that explicitly. It sets the operating point VDS. But in this case, whatever transistor I have, I will go on varying VGS until I come to 200 microampere of current and stop there. So that means that I am operating with a fixed ID. Okay, so that is ID, I have chosen that to be 200 microamperes instead of choosing VGS to be 3 volts. Okay, so what happens in this case? I know that the convenient expression to use in this case is square root of 2 times mu1 Cox W by L times ID. What happens if there is a change in the threshold voltage, that is the new value of Vt is the old value plus delta Vt? Nothing, because this expression doesn't have Vt at all. Okay, so Gm prime will be the same as Gm. This is assuming that the current has been maintained at 200 microamperes. And let's look at if Kn, the current factor, changes to a new current factor Kn prime, you see that this expression for Gm has Kn inside the square root. The ratio of new Gm to the old Gm would be square root of Kn prime by Kn. Okay. So putting all these things together, we can see that if you fix the drain bias current ID, the variation in Gm is a lot smaller. Let me put everything into a table. Okay, when I say fixed VGS, I mean that VGS has been calculated for some nominal value of Vt and Kn. That is, I assume some value of Vt, say 1 volt, and some value of Kn, say 100 microampere per volt square. I know the Gm value that I want, so I calculate VGS. And in our example, it was 3 volts. And for that, the current would be 100 microamperes. Now, the problem we are facing is follows. When we buy many transistors or operate the same transistor at different temperatures, I won't have Vt to be the same and I won't have Kn to be the same. These will all be different. Okay. The question is what to do in these situations. Should I keep the gate source voltage fixed, or should I somehow make the same current flow through the transistor? So let's examine these scenarios. So if we keep a fixed voltage, something will happen. If we maintain the current to be fixed, something else will happen. First, let's look at what happens when the threshold voltage changes by delta Vt, but Kn remains as it was. We have already evaluated this. The ratio of the new Gm to the old Gm is 1 minus delta Vt by VGS minus Vt. Okay. And in this case, in case of fixed ID, this is just 1 because Vt has no effect at all. Similarly, if I consider the change only in Kn, what happens? The ratio of new Gm to old Gm will be the ratio of the current factors, whereas in case of fixed ID, it's the square root of the current factors. So it's very easy to see that Gm prime by Gm is much closer to 1 in this case. Okay. First of all, in case of Vt change, there is no effect at all, which is great. Okay. And in case of current factor change, we have the square root. Okay. So let's assume that Kn prime is 1.1 times Kn. Okay. That is, the current factor has increased by 10%. So then in this case, this number will be 1.1. Gm also increases by 10%. Whereas in this case, this will be approximately 1.05. I assume you know this relationship. For very small values of x, square root of 1 plus x is approximately 1 plus x by 2. So, square root of 1.1, which is square root of 1 plus 0.1 is 1.05 approximately. Otherwise, you can calculate it using a calculator and see, it will come out to be close to this. So, although the current factor changes by 10%, GM changes only by 5% in this case. So, this biasing, fixing the value of VGS, although that was kind of natural and that's what we started with, is not a very good way of doing it. Okay, it is not very robust, and GM changes quite a lot with temperature and with different devices, whereas in this it also changes but by a lot lesser amount. Okay, so what we need to do now is to find out ways of biasing the transistor where the current will be fixed, not the gate source voltage. Okay, we will see how to do that in the forthcoming lessons.